Okay, so this one's chapter 19, and this is going to be titled "The Nucleus: A Chemist's View." Really, this is nuclear chemistry. That's what it's typically known as. And an interesting side note to this is there's actually very few programs if you want to go to a master's or PhD level school. The vast majority of people that get trained in nuclear chemistry onto a PhD master's level, the higher level engineers, those sort of people that you've heard of, typically actually get trained by the Navy or the Air Force, depending on what branch they come up through. The largest number of nuclear engineers and chemists and everybody that works in nuclear is actually trained by the US Navy, which has probably the best program in the world. But, anyways, this is your sections here. So, you may remember our nucleus and our nuclear model of an atom. And the nucleus is composed of a collection of what is called nucleons. And that's the individual nucleons, multiple. This is subdivided into your two components that we normally associate with the nucleus, which is our neutrons and our protons. Remember, neutrons are the neutral atomic mass 1. Protons are the positive 1 atomic mass 1. Both of these are called nucleons when you don't want to specify what you're talking about. So these are actually composed of smaller particles that we call quarks. We're not really going to go into that at all. And this is actually much more cutting edge theories at this point. And yes, it is theories at this point. There is not law or anything. So the composition of a neutron or proton, we're not really going to go any further into it. I'm just going to tell you that one of the theories is they're composed of quarks. There are other opposing theories, but it's a pretty good theory. I actually think that's probably about right. Anyways, the atomic number is going to be denoted by Z. And you guys have actually seen this atomic number before. So if you think back to when we were talking about the different periodic properties of our periodic table, this atomic number actually shows up there. When we talk about the strength of the magnet, we call a nucleus, right? And the reason that is Z, that symbol shows up there. Of course, you should hopefully know atomic number, which is the number on the top of each of the boxes in the periodic table, right? I guess I just assumed that. Number of protons in a nucleus is going to be, of course, our atomic number, right? Just like we have talked about hundreds of times throughout your chemistry career. Mass number, this is actually denoted by A, and this is the sum of the protons and neutrons in your nucleus. Or otherwise, this would be called the number of nucleons in your nucleus. And that's because those two are the major components of your mass. They're 99.9999 something percent of the mass of your entire atom. The electrons essentially don't have any significant amount of mass. They do have mass, just not a lot. Isotopes. You guys know this one as well. These are atoms with identical atomic numbers, but different mass number values. And those different mass number values come about because you have different numbers of neutrons. Now, you may have been wondering why exactly those isotopes occur, how they're possible, these sort of factors, and this is the chapter where you get to find out. So, right here, this is a nuclide. This is the singular form of a nucleus. So, nucleus is multiple nucleides. So here we have a nuclide, and this is an example of how you denote what a nuclide is. This is going to be a unique atom that we represent by these symbols. So X is going to be your symbol of your element. That's going to be Fe for iron, C for carbon, O for oxygen. Those are the things that show up in your periodic table, right? Your symbols. A, which is on the top left, is going to be your mass number. So remember, this is for a nuclide, a single one. And so this is always going to have a whole number because it's going to just be your number of neutrons plus protons. Z, this is going to be your atomic number. Now, you will notice if you're paying attention here that X, your symbol, is actually determined by Z, which is your atomic number, which is however things order on a periodic table, right? So if you have an atomic number of 1, this is hydrogen, isn't it? Now, that means that if you're paying attention here, you don't actually need to write down Z. You will see many chemists, physicists, really most people will end up just not writing Z. And that's because this symbol here, carbon, hydrogen, oxygen, that actually tells you what this Z is if you just look on a periodic table, right? Or you happen to have it memorized. So the nuclear stability, thermodynamic stability. This is the potential energy of a nucleus compared with the sum of the potential energies of its constituent neutrons and protons. Kinetic stability. This explains the probability of radioactive decay of a nucleus. These are the same terms as before, just applied to nuclear stability instead. So remember, thermodynamic stability is whether you're exergonic or endergonic, right? It's going to be whether you're likely to fall apart or whether you're likely to stay together. The kinetic stability just says how long it's going to take. So if we're talking about something being radioactive and not stable, typically we're talking about happening in a human lifetime, right? And so in the lab, something that would fall apart after 1,000,000 years, you're not really going to be too worried about that harming you. You're going to be pretty safe. Whereas something that falls apart in the matter of days, well, that's going to be an issue, right? You're going to start getting these splitting while you're working with them. Now, radioactive decay, this is the nucleus undergoes a decomposition to form a different nucleus. This happens when your nucleus is not thermodynamically stable. So there is what is called the zone of stability. You may hear island of stability sometimes, or archipelago, if you will, or there's a number of different sort of analogies that people use for these that you end up hearing people call it. Okay, so zone of stability right here, this is where you find stable nuclei. That means nuclei that will not fall apart. And so this right here is going to be a function of Z and A. So as the number of protons in your nuclide increases, the neutron to proton ratio required for the stability also increases. So right here, for example, this graphic has a lot of information on it, like I mentioned before when in these lectures. Really, the graphics tell you everything you need to know about a science concept. Right here we have a 1-to-1 neutron to proton ratio. You'll see for the light atoms that almost directly correlates with our zone of stability. But as we go up here to the heavier atoms, as we get more and more protons, you're going to start seeing that it's going to drift further and further from a 1-to-1 ratio. And so right here, this is your number of neutrons. Up here, this is your number of protons. And you see that when you get heavier, you want more neutrons per protons. So instead of being a 1-to-1 ratio, you'd be something like a 2-to-1 ratio when you start getting up here. It's not necessarily a 2-to-1, but you get the idea. It's like a 1.29 to 1 ratio for cadmium right here. Now, these are stable nuclides. That means they are not radioactive. They do not fall apart. The ones off of this zone of stability, if you're off the zone of stability on either side of it or further up here, these right here are not stable. That means they're going to fall apart given enough time. So they will eject parts of the nucleus given enough time. And so right here, you'll see, if you pay attention very closely, this corresponds to, well, here's 80, right? So this corresponds to just past 80. You'll notice this actually corresponds to lead. And that is actually, on your periodic table, your last stable nucleus, or nuclide in this case, because it's a single nucleus. Now, everything after on the periodic table is not stable, it's radioactive. And you'll see that there's actually different forms of and isotopes of these nucleuses, of these elements, that are actually radioactive. And that's because they have the incorrect ratio of protons to neutrons. All right, so radioactive decay. Let's go through some observations. So all nuclides with 84 or more protons are unstable with respect to radioactive decay. They will eject particles from the nucleus or capture particles in the nucleus to try to establish back onto the zone of stability. Okay? They will have an equilibrium that is shifting towards going the zone of stability, if you will, right? So when neutron to proton ratio equals 1, the light nuclides will be stable. So those first nuclides, the first part of the periodic table, those will be stable with a ratio of 1 to 1. For the heavier elements, the neutron to proton ratio required for stability is going to be greater than 1 and increases with increasing Z, or increasing number of, excuse me for the pause, I needed a drink. Man, my throat is weird today. Increasing number of protons. So there's certain combinations of protons and neutrons seem to confer special stability. So nuclides with even numbers of protons and neutrons are typically more stable than those with odd numbers. Certain specific numbers of protons or neutrons produce stable nuclides. These magic numbers, and that's what this is coined as, magic numbers, because originally when they came up with these numbers, they figured them out, but they couldn't figure out why. And so it was magic numbers, right? And these magic numbers is 2, 8, 20, 28, 50, 82, and 126. Now, the reason for why this is, I'm not going to go hugely in depth on this. Actually, it's a very advanced subject when you start going really in depth on nuclear chemistry. Honestly, it is something you can get an entire PhD out of, right? And you still won't even know everything there is to know about it, because humanity has just scratched the surface. We just entered the nuclear age, and a lot of development was actually halted due to, well, we stopped making nuclear bombs. That was where a lot of our development came from. And interestingly enough, one of the fathers of nuclear reactors sort of conned the government into trying to make a plane with a nuclear reactor on it. And so they'd research his research project. Originally, the Air Force, Navy, and Army all had their own version of a nuclear reactor they were trying to make. And the one being made by the Air Force was by far and away the superior concept for a nuclear reactor. Would have been a much better thing to have. But the fact that they thought they were going to mount that on a plane was just silly. It was he kind of caught the government on that. I'll give them that. Anyways, types of radioactive decay are the alpha particle production, spontaneous fission, beta particle production, positron production, and gamma ray production. So let's talk about the alpha particle production first. All right, now this is going to involve a change in your mass number for the decaying nucleus. First, you need to understand what an alpha particle is, though. So alpha particle, or you can put the symbol for alpha, well, the Greek letter, I should say, not really a symbol. Alpha, of course, particle. And this is actually a helium nucleus, okay? And so a helium nucleus has two protons, two neutrons, has a atomic number of 2, a mass number of 4. And so you can denote this helium nucleus that you're shooting out of your nucleus of your larger atom as an alpha particle, or you can just call it a helium nucleus. Now keep in mind, you're shooting this thing out of your nucleus, right? There's not going to be any electrons on it. So it isn't really a helium atom at that point. It's a helium nucleus. You don't have any electrons with it. Of course, if you get near electrons, it will take them up, and they'll be attracted to it. So, but you get the idea that this is just a nucleus for a helium atom being ejected out, usually at fairly high speeds. So this is the common mode of decay for heavy radioactive nuclides, because you're going to reduce this mass number by 4, and that can bring you further down to the 84 limit of being stable, right? And so this is one of the ones you have to do the most when you're something like 92 atomic number, which is 8 higher than anything that will ever be stable. So this is a great example of an alpha particle decay. It's actually one of the most useful examples of this. It's one of the most ubiquitous ones, which is uranium-238, which is another way you can write the uranium with a mass number of 238. And uranium, of course, has an atomic number of 92. This right here is the reaction for a nuclear decay written in long form. And right here you see that you are ejecting an alpha particle, which again is a helium nucleus. And this leaves you with, well, you have to have the same mass and atomic numbers on both sides. So you see that you had 238 here. This is going to then be 234 remaining, because that's minus 4, right? And that atomic number right here, 92, minus 2, because you ejected 2 out of this, is going to give you 90. 90, of course, is thorium, Th. And by the way, what heats the inside of the Earth, what's the actual energy source for heating the Earth? Yeah, convection currents, lava, and all that recycles the energy. But what the actual source of energy is this nuclear decay we're looking at right here, actually. This is one of the major sources of heat inside of the Earth. So spontaneous fission, this is going to be splitting of a heavy nuclide into 2 lighter nuclides with similar mass numbers. This occurs at an extremely slow rate, and I've seen many general chemistry books that don't even mention this, because it's so slow that when it comes down to it, the other forms of nuclear decay are just so much faster. This almost becomes something you don't even have to talk about. But it does exist, and it is important, and it is interesting. So there you go. So you'll get lighter nuclei out of it. Beta particle production. Of course, this can be denoted with the beta Greek letter. The mass number of the decaying nucleus will remain constant. The net effect is to change a neutron to a proton. You might notice the difference between a neutron and a proton is a neutron has no charge, 0 charge. A proton is positive 1. Well, what has a negative charge, which is the difference in these charges, right? Well, that's an electron, isn't it? Okay, so what you do in a beta particle production is you literally shoot out a high energy, very fast moving electron from your nucleus when you convert this neutron to a proton. And so nuclei that lie above the zone of stability, so right above, are expected to undergo a beta particle production, or be a beta particle producer. So the emitting nucleus does not contain electrons, even though the beta particle is an electron. Again, remember, this is going to be shot out of the nucleus. It is going to have a lot of energy. It's a bit like a rocket escaping Earth, right? It's moving fast enough that it escapes the attraction. Gamma ray production. Again, this is the Greek letter gamma, gamma ray. You may notice, if you remember your previous chapter in General Chemistry 1, that in the electromagnetic spectrum, the highest energy photons, the highest energy light, if you will, was gamma rays. And yes, this is the same one. This is gamma rays, just like that. It's one of the, it's part of the spectrum for the electromagnetic spectrum, which we usually consider to be light because visible light's on that one. They're very, very high energy photons. They're very, very high energy waves. So gamma ray production accompanies nuclear decay and particle reactions. Typically, these don't happen by themselves because they're not going to change your mass number. Because again, they're just energy. They're a photon. So they're going to be you expressing a very large amount of energy being shot out as a photon. Well, large for a single atom. So right here you have uranium. It's splitting into an alpha particle and thorium. And you see here it actually emits 2 gamma rays while it's doing so. Again, gamma rays don't have any mass. They don't have any charge. So no atomic number, no mass number. They're just energy. They're just photons. So there you go. Positron production. You may have heard of a positron emission tomography or a PET scan before. By the way, saying PET scan is really stupid because a tomography is actually a type of scan. But that's actually how you're supposed to say it. So it's like when you say PIN number, personal identification, number. So keep that in mind the next time a doctor says PET scan to you, you can get a little chuckle out of it. Of course, when they give you the results of the PET scan, hopefully you'll still be chuckling because nothing's wrong. So, this is a positron production. That's the positron from PET scan. This occurs for nuclides that lie below the zone of stability. So these nuclides would have small neutron to proton ratios. A positron is actually a form of antimatter, which a lot of you have probably heard of antimatter before and thought it was something, really exotic and there's no way I'd ever encounter it. But most of you probably have encountered it in your life. So a positron is going to be a particle with the same mass as the electron, but with an opposite charge. Hopefully this doesn't take a lot to remember, because they both have tron, and this one's positive, while electron is negative, right? So it's going to be just the positive form of an electron. Yes, it is antimatter. If it runs into an electron, they will annihilate each other and turn into energy. So yes, that will convert mass to just pure energy. And yeah, if you had a bunch of positrons or a positron beam, yes, you could create quite a bit of an explosion because they would convert to pure energy. But remember, positrons have very, very little mass when you're talking about a single positron. And so just a small amount of positrons being released, like a PET scan, doesn't cause a lot of damage because that's a very small amount of mass, which will give you a very small amount of energy. So the net effect here would be to change a proton to a neutron. You're literally ejecting the positive charge from a proton to form a neutron. This causes the product nuclide to have a higher neutron-proton, so you're reducing that number, ratio than the original nuclide. Positron, of course, is the antiparticle, antimatter version of the electron. And so when they annihilate, so when a positron collides with an electron, this is going to transform into electromagnetic radiation in the form of your high energy photons, which we typically are going to get gamma rays. Of course, when you're doing a PET scan, this is actually what you're looking for, is how fast your positrons, which is right here, +1 charge, collides with an electron, and would give you a burst or gamma ray. So this is a characteristic of matter-antimatter collisions. Anytime you have a collision between matter and antimatter, they will annihilate each other and produce bursts of gamma ray, uh, which would be energy. Now this burst of gamma rays, this can then heat things up. It can do all sorts of things. So yes, if you have a large amount of antimatter, yes, it would cause a lot of energy. A small amount of antimatter doesn't cause that much energy. So electron capture, or K capture is another way of calling this. This process by which the nucleus captures one of the inner orbital electrons. You may have noticed that before we sort of hand wave this away by saying, oh, there's a node between the orbitals of electrons and the nucleus. And yes, this doesn't happen very often, but it can happen where an electron will actually run into your nucleus, and this is going to be an electron capture if this happens with all the right energies and just the stars align, if you will, or the thermodynamics align, if you will. And here we see an example of this, of course. Notice right here again, because this is an electron, mass number 0, and it has a -1 charge. Now, this negative charge for an electron, that's going to be what we put for its atomic number, because this number right here, this atomic number, we're actually keeping track here of the charges, just like we did in every other chemical equation. So right here, we start with a 201 and 80. We'll have the same mass number, but our atomic number goes down by 1. And so we get 79. This will actually produce a bit of energy, and so this will produce a gamma ray as well. And this is just an expression of the gamma ray being released as a release of excess energy. So let's write balanced equations for each of these following processes. Right here we have carbon-11 producing a positron. Then we have bismuth-214 producing a beta particle. And a neptunium-237 producing an alpha particle. I usually have to pause and think sometimes with these higher on the periodic table ones. I don't get to use these a lot. Only one chapter in my entire year of teaching. All right, so we must find the product nuclei represented by the A, Z, X in our following equations. So what we do here is we of course start with what's doing this nuclear producing, right? So in this case, positron production. Now this is that carbon-11, and so we write out the carbon-11. We put an arrow, and of course this came from the problem itself, so we can just copy that directly from the problem. We're producing a positron, so we should have that memorized. We should understand what a positron is. That's really the meat and potatoes of this chapter. And so a positron is going to have a mass number 0 and a +1 charge. Remember, it's the anti-electron. Now, this is going to be plus some symbol with the mass and then the atomic number. So how do we find this mass number? Well, we had 11. It released 0, so we're still going to have 11, aren't we? So what's the atomic number here going to be? We started with 6. We released 1 positive charge, so that has to be 5, because 5 plus 1 equals 6. All right, so we get that is 11, 5. We look it up on the periodic table if we don't remember it, and that would be our B, or boron. And so this would be the complete balanced equation right here. And that's that. So, knowing that beta particle is represented by 0, -1, and then we put E for an electron, we can go ahead and do the same thing as we did before. So we have our 21483 Bi that we came from the problem. Again, we write that is producing products. a 0, -1 electron, because that is a beta particle. Plus, well, we get 214 here. It released 0, so it's still 214. This is 83. It released -1. So this has to be 84. Because remember, this plus this has to equal that. So 84 minus 1 is 83. So if we look up 84, this is PO. Right there on our periodic table. So the next one, we're going to go ahead and do C. This is a release of an alpha particle in this case. So remember, an alpha particle is 4,2 helium. And so we write that in. We have this from the problem. We released 4,2 helium. This number right here has to go down by 4, which is 233. This number here, which is 93, has gone down by 2, which is 91. And then we looked up on the periodic table, and that is PA. And that is the problem. Decay series. So you may notice that there's a lot of these atomic numbers and mass number, atomic number combinations that a single reaction, a single nuclear decay, simply will not handle. We can't go, for example, from uranium, 92, down to lead, 82, with a single nuclear decay. An alpha particle just isn't going to do it. And so what we have is a decay series. So when radioactive nucleus cannot reach a stable state via a single radioactive decay process, we get a series of decay processes, which we can call a decay series. And this will occur until you establish a stable nuclide. Now, interestingly enough, this decay series can be predicted based on what is going to be closest to your island of stability, or your stability zone. And this is actually how you come up with these nuclear decays. And actually, it's kind of an interesting field if you're curious. This right here shows you a series of decays here, and then it gives you this eventually. This is actually what happens inside the Earth. This right here is the most ubiquitous source of heat in the inner Earth, right here. Thorium breaking down to lead. That's actually the majority of your nuclear heating period of the inside of the Earth. All right, so right here we see the decay series, and this is what a decay series looks like. From uranium-238, which is what we looked at before, down to lead-206. And so here you can see the mass numbers. And that's 238 here, 234s, and right here you can see your atomic number. So for example, this is 92, these are uraniums. This right here would be 91, atomic number. This right here would be 90, which is thorium. And so these are different isotopes of thorium. These are different isotopes of uranium. All right, now, when you're going down and to left, an alpha particle being ejected, that is going to cause you to lose 2 atomic numbers and 4 mass numbers. And so that's why it's down to the left like this. A beta particle being ejected is just going to cause you to gain an atomic number. And so you go from 90 to 91 to 92. And those are beta particle ejections. Now right here, again, we have more alpha decays, some beta decays going across, and then an alpha decay, beta decays going across, and then alpha decay. And you'll see that this is actually a fairly common thing that happens when you go from the heavy to lighter. This is because you're getting closer to your zone of stability right here. So it's sort of bobbing back and forth around it. Anyways, and you can predict which will happen due to the zone of stability and your magic numbers. Those are the two ones that let you predict what's going to happen here. All right, so what is the approximate ratio of the atomic radius to the nuclear radius? Well, that'd be 10 to the 5th. And the easy way to remember this is about 100,000 times difference. If you want that in a sort of visual representation, if you take a tennis ball and place it in the middle of a football field, that tennis ball is going to be your nuclear radius, and the football field would then be your atomic radius. And that's that difference. It's massive, right? And that's why the nucleus is so small. And if you remember back to when we talked about the nucleus originally, you'll actually remember that we actually talked about these different nuclear decays to some degree, and we used that to build up our knowledge and understand how they came up with the idea of a nuclear atom. Hopefully you did that. There's a number of you I didn't have, but hopefully they did that. That's good science teaching, so that you become scientists and can try to disprove theories as a scientist should, instead of just parroting what you've been told. So identify the missing particle in the following equation. So again, we're just going to have both sides adding up to the same numbers. So here we have 238. This would be 4 according to our periodic table. And so this means this would be 234. This would be 92. This is 2, so that has to be 90. And so that has to be C. Carbon 11 is an unstable isotope. Which kind of radioactive decay would be expected for this isotope? So what you want to do here is you want to have the least amount of work to get to a stable isotope. And that is going to be a positron production, ejecting a positron. And the reason for this is remember that on the light atoms, those first two rows essentially, and a little bit beyond that actually, you're going to want a 1-to-1 ratio of protons to neutrons. And so if you look back at your proton to neutron ratio of carbon, carbon has an atomic number of 6. There you go. Sorry, I had to get a drink while I was going from one to the other. I don't know why that lengthened out like that. Anyways, so we have atomic number of 6. What we want is to bring that down. We want to reduce that number from 6 closer to the 11 or 5 in this case. So electron capture transforms potassium-40 into what nuclide? And so you think about electron capture, that's going to be taking on negative charge. That means one of the protons is going to be turned into a neutron. So your number of protons, your atomic number, is going to go down by 1. While your mass number isn't going to change because, again, that is your number of protons plus neutrons. And so we, of course, still have the mass number 40, but now we move over one space to the left on the periodic table, which wraps around the other side, which will be argon. So when U-235 nuclei is struck by a neutron, the products are 2 neutrons, Ba139, and what? And so what you're doing here is you're just adding stuff up to get to 235, aren't you? Or the easy way to do this is 235 minus 2 neutrons, so that number goes down from 235 to 233, minus 139, and that will give you 94. And then you are going to take Ba, you look it up on your periodic table, subtract it off of the value for U for the atomic number, and that will give you the value for Kr if you look on your periodic table. So the rate of decay, this is defined as the negative of the change in number of nuclei per unit time. Or another way of thinking of this is typically this would be you'd talk about disintegrations per second or disintegrations per minute, i.e. how fast do your atoms disappear? They don't actually disappear, of course, they just change form, right? But they're referred to as disintegrations because they're falling apart. The rate is directly proportional to the number of nuclides in a given sample. So your change in nucleides is going to have to be proportional to those number of nucleides. Now, the negative sign indicates that the number of nucleides is continuously decreasing. The rate law for a first order process is going to give you this same relationship. So this is a first order process. And so yes, rate equals negative delta n over delta t, which also equals a constant times the number of nucleides, which is your first order process because it's power of 1, or first order, right? So the integrated first order rate law, way back in the kinetics chapter, my goodness, it came back, but guess what? You only have to use this one. You only have to use first order rate laws for all of nuclear, okay? There is no other rate laws you have to deal with. So this is your integrated first order rate law, which is the natural log of n, which is your number of nucleides remaining at this time, and n0, which is the initial time zero number of nucleides. This will equal negative k, which is a number that you have for each species or each isotope of an element. By the way, if this k, for a stable isotope, there won't be a k. It won't disintegrate, right? It won't decay. This right here, of course, would then be time. The amount of time that you would get this number. Now, we talked about half-life in these previous chapters, and that was T1 half, right? And so we can plug these in and get a time half or a half-life based on a set number, which is a constant over a constant, right? Or natural log of 2, which is 0.693, divided by k, which is a constant for each isotope. So this helps in determining of a rate constant. We can literally just wait until half of our sample disappears, and that'll be our half-life, right? So in a first order process, that time 1/2, half-life, this is a constant value. It doesn't change because it's composed of two constants. You always have the same half-life for any given isotope. All right, now, an interesting side note to this is, yes, you have probably heard of the nuclear clock, which is the standard upon which all time is based now. That's the world clock, is a nuclear clock. Yes, this does take into account half-lives. That's actually what that uses. It uses a half-life of cesium, if I remember correctly. I haven't looked it up in a while, though, so you may want to look it up. Actually, I haven't looked at if they've changed it in probably a decade. I don't think they did, though. Yeah. Anyways, the half-life actually will tell you how long you would have to wait to get to half that sample, right? And so you can base time on that. It's a clock. It counts down. So if you half a sample, that's going to take your half-life. If you half it again, it's going to take that same amount of time. If you half it again, that's going to take that same amount of time, right? So again, that's that half-life. So the right here we have a bit of an example. So the half-life of molybdenum-99 is 66 hours. How much of a 1 milligram sample of this isotope is left after 330 hours? And so what you do is you just need to count down the number of half-lives, right? So I actually showed you examples of how to do this in the previous chapter, but I'm going to go ahead and show it again because I bet a lot of you have forgotten it by now. Because frankly, there's been quite a bit to learn, right? So the rest of the stuff probably forced it out of your head by now. So remember, if we look at 330 hours, so how many sets of 66 would that be? Well, 6 times 5 is 30, right? And so that is going to be 5 half-lives. And so we need to undergo 5 half-lives. So we half it once. That'll be 66 hours. So half life is going to give us half our sample remaining. And so we have 0.5 milligrams remaining. We do another half-life that's going to be 132 hours, right? And that will give us half of our 0.5 remaining. So 0.25. We undergo another half-life, our third one, and we were going to have half of that, which is 0.125 milligrams. We do it again, that'll give us 4 half-lives, and we'll have 0.062 milligrams. And we do it one last time for our fifth time, and we have 0.031 milligrams. And so yes, that will be the remaining amount after 330 hours. You notice that's actually quite simple and easy. We don't have to do any complicated math. We can just sit there and half. I actually prefer that method. I usually find that it's a lot easier than having to do any math or look up my integrated rate law or anything like that. So krypton consists of several radioactive isotopes, some of which are listed in this table. Which of these isotopes is most stable, and which isotope is hottest? So how long does it take for 87.5% of each isotope to decay? So the first thing we need to think about is, when I'm talking about hottest, remember this is a thermodynamic process. So hottest means it's going to have the most energy breaking off at any given amount of time, right? And so a faster half-life is going to give you more heat. Literally, it's going to heat up everything around it because it's releasing gamma rays and energy, which is heating everything around it. It's releasing energy. So the most stable one is going to take your longest time, right? And your hottest one is going to take the least amount of time. All right, and so there's your deals. So let's look at how much time it takes for 87.5% of each isotope to decay. And so we look at the krypton 73, and again, that's your hot one. Now, what we have to look at is 87.5% of each isotope to decay. How many halvings is that? So if 87.5% of it disappears, decays, that means you're left with 12.5%, right? Which is, okay, so remember, the first halving is going to be 0.5. The next halving, the second halving, would be 0.25, right? And then the halving after that, the third one, would leave us with 0.125, which is what we're left with here. And so we have halved this 3 times. So we look up here at the half-life we were given for our fastest one, 27. We multiply that by 3, and we get 81 seconds. We do the same thing for krypton 74, which is our longest half-life, and that's going to give us 34.5 minutes. Sorry, read the wrong one. That'll give us 6.3 times 10 to the 5th years for our longest one. Anyways, here's all of them on the table, just worked out for you. Again, that's just your 3 half-lives times 3 for each of the half-lives, right? And that's a very, very long time. That's hundreds of thousands of years to half that sample to get that 12.5% left. Hopefully you aren't trying to wait around for that. So, cesium-131 nuclide has a half-life of 30 years. After 120 years, about 3 grams of a sample remains. What was the approximate original mass of that cesium-131 sample? So remember, you have half-life of 30 years. So after 120 years, that's going to be 4 half-lives, isn't it? Or 4 times 3, 12. Now, that 4 times halving, that means that you've halved this 4 times to get to 3 grams. So all you have to do is just double it 4 times, and that will give you your original mass. So 3 times 2 times 2 times 2 times 2, which gives you 50 grams. By the way, keep in mind that there's no period here, so we're actually rounding the ones place. Yes, you will give on your calculator 48. That rounds to 50. All right, so nuclear transformation. This is going to be changing of one element into another. This was observed by Lord Rutherford when he bombarded nitrogen-14 with alpha particles. And so this is what he observed right here. Bombarding nitrogen-14 with alpha particle gave him oxygen-17 and a hydrogen. So the transformation of aluminum to phosphorus is another example of this. Here we again are bombarding with an alpha particle to get phosphorus and a neutron. Yes, you can make radioactive elements. This is actually how some of the radioactive elements are made. When we're talking about anybody, if you've ever been in a hospital, you'll see that there's a radiology department. That radiology department typically has various radioactive elements they need for several different diagnostic tests, and sometimes as a source for radiology treatments, which is a fairly unusual thing, but there is radiology treatments. Anyways, these sources are typically made through this process, which is nuclear transformation. No, these do not have to take part in some sort of hadron collider or huge colliders, though some of them do to make very exotic molecules or atoms. However, typically what you do here is you would just take a piece of uranium or similar alpha particle producer, and you would literally put that in a block of lead with a small hole on one end, which you'd normally keep covered so you don't die from radiation exposure. But you would then unblock that hole to let alpha particles shoot at your sample and thus bombard them, right? That's how you do true nuclear transformation, if you're ever curious. However, the most famous example is obviously a particle accelerator. So a particle accelerator, this is a device that's used to provide particles high velocities. And these high velocities are going to achieve something that just touching the particles together cannot, which is, remember, your particles here oftentimes are going to be the same charges. So, for example, your helium nucleus and your nitrogen nucleus are both positively charged. So if they're not approaching each other at a very, very high speed, they will not overcome that repulsion, and they'll never actually touch and collide. However, if you can get them at very high speeds, you can cause the collision, which will not only cause them to actually touch, but will actually cause them to fuse together. And that is an example of a nuclear transformation. So particle accelerator facilities are nuclear transformation, can facilitate a nuclear transformation when positive ions are used to bombard particles. These are enabled by the presence of electrostatic repulsion between the target nucleus and the positive ion. Transformation occurs when a particle overcomes that repulsion and penetrates your target nucleus. So right here we see a cyclotron. This is an example of a particle accelerator. This is typically a much more contained particle accelerator than you may have seen in the news or any stories you may have seen. Typically they tend to show you the several country spanning CERN particle accelerator. They don't typically show you the workhorses, which are things like cyclotrons, which are typically much smaller and contained in like a football field size-ish. So an ion is introduced at the center of the device, which is right here. This is your ion source. The device will accelerate the ion in a spiral path to keep the area that you have to run across lower by using alternating electrical fields. It's a lot like a electromagnetic train, one of those high-speed trains you'd find in Europe and Japan. And so this is going to alternate in electric fields in the presence of a magnetic field, which will cause the electron to continuously, or the particle here, to continuously accelerate. You'll get into a fraction of the speed of light. Any fraction of the speed of light is extremely high energy. By the way, yes, this does take up a lot of energy to do, if you're ever curious. And then you will exit onto a target, which will be your bombardment. Now, when you do this, typically these have a vacuum. These are vacuumed out because anything in this cyclotron is going to cause collisions, and then you'll lose all your energy. So right here, this is the schematic of a linear accelerator. So right here again, we have our ion source, and we have our varying electrostatic fields, and you get the idea. You don't really need to know that much about this. It's just something interesting that will give you a bit of background. And, maybe you look at this information and you go, hey, I want to be a nuclear chemist or a radiologist or, something. So, fission reactors. This is the most common source of neutrons that can be used as bombarding particles to affect nuclear transformations. Neutrons are uncharged and cannot be repelled by electrostatic force. Easily absorbed by many nuclei, leading to new nuclides. So they're very easy to get in. They don't take as much energy for the bombardment. It's just much more efficient. And they can not only give you fission, which would be split. They can give you splitting things apart. They can from heavier nuclides. They can also give you slightly heavier isotopes by doing this off of a fission reactor. Of course, even then, the fission reactor itself could also be used to provide energy, which is, very nice. So, more efficient. The neutron and positive ion bombardment. This is going to enable scientists to extend our periodic table. And this is where you get those new atoms at the end of the periodic table that right now many of them don't have names, because it's actually a process to go through to name them. And we've been pretty consistently extending that periodic table over the last 20 years, though it has slowed down a little bit because it's starting to get somewhat energy inefficient. This is the trans-uranium elements, which is everything after your uranium. These have atomic numbers that are greater than 92 and have extremely short half-lives. So the chemical characterization of these elements is extremely difficult, and that's why we really don't know for most of those any chemical properties of them. So right here we see some different examples, our synthesis of some of the trans-uranium elements. So for example, you get neptunium by taking uranium-238, bombarding it with a neutron, which gives you your neptunium, and an electron being ejected. And that has a half-life of 2.36 days. And here's some other different ones. There's americium, named after America, of course. Rutherfordium, named after Rutherford, California, because americium was already taken. So California. By the way, one of the best nuclear facilities in the entire world is located in California. Berkeley is a very, very, very good nuclear program, if you're curious. One of the very few college-run nuclear programs in the world. The conversion of one element into another. So what is the conversion of one element into another? Is it going to be a chemical reaction? No, we don't ever convert elements in a chemical reaction. We just change how they're bonded to each other, right? Is term nuclear transformation? Hey, yeah, that actually makes sense. Yeah, that's actually what it's called. Was a dream of alchemists, but is impossible. Well, yes, it was a dream of alchemists, but it is possible, actually. We've done it. So, yay. All right, the measuring of radioactivity levels. Or, oh my god, I just got dosed with radiation. I'm going to die. So the Geiger counter, or the Geiger-Muller counter. Mueller really got sort of a tough stick here. Everybody calls it the Geiger counter. It was co-developed. So this capitalizes on the fact that high energy particles from radioactive decay produces ions when they travel through matter. So literally, the gamma radiation, those high energy photons, when they hit an atom, they have so much energy that they will eject an electron from it. So you have a probe on the front of a Geiger counter. That's the little wand. If you've ever seen the movies or seen a Geiger counter in person, you have a box and a wand. And the Geiger counter, yes, as that thing goes tick, 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 and faster ticks, the more you go, oh my God, there's a lot of radiation. Um, so that probe on the end that actually has argon gas in it. And this argon gas, when it is bombarded by high energy particles, is going to cause it to eject an electron. And that electron is going to be picked up by the wire running through the probe, which then runs to the box. And the box is actually where you're going to get an amplification effect on that electron that gives you a signal. And so, literally, in the old Geiger counters, you had that probe and it actually did all the work. And then you had an amp, like you would a stereo system, an amplifier, and that's hooked to a speaker in that box. And then the vast majority of the weight of the box in the old systems was actually the battery, and that's that little handle, and then it had a little box under it. That's actually why it looks like a box, is because there's a battery mostly, and it just has a little amp and a little speaker on it. Anyways, of course, they have become much more technically proficient. Many of the new Geiger counters still have the argon gas, but then they're hooked up to a digital system, and so really the wand is it. You really don't have that much over other than the wand if it's a newer Geiger counter. You know it's pretty old if it's any bigger than a wand. And they've actually made even newer, I quote unquote, Geiger counters, which are solid states and don't even have argon gas in them. There's uh, quite a variety now. They've really gone over the years. This has progressed tremendously because people kept trying to sneak dirty bombs into the United States, and they spent more and more money on research to detect, radioactive particles. So the formation of ions and electrons by the passage of high energy particles is going to facilitate a momentary current flow. And in the old speakers and analog devices, you measured the flow of electrons rather than individual electrons. So the electrical devices, like a speaker, for example, can detect this current flow, and the number of these events, tick, 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 can be counted to determine the decay rate. And so if you had rapid ticking, you knew you had a very high decay rate around you. Or in the newer ones, it would literally show you a number for how fast it's detecting them. Scintillation counter. This is going to capitalize on the fact that some substances emit light when they are struck by high energy radiation. And so literally scintillation, as in light, counter. All right, right here we see our Geiger counter, and this is literally that probe we were talking about, and then this would be the casing with the battery, the speaker, and the amplifier. This right here is actually one that has both a speaker and it has a dial showing the count. And there you go. By the way, you need a wire coming back here to put electrons back in here, to pull electrons back onto your argon atoms and reset them, so you can be ready for the next wave, if you will. Carbon-14 dating, or radiocarbon dating. This is going to be based... Oh, by the way, an interesting side note here that you may not have known is radioactivity is literally what it says. So radio waves being produced by a substance, because the breakdown causes ejection of electromagnetic radiation, which literally will cause pops and hisses if you have a radio detector. Uh, you know, like a phone, or if you had a radio, or any of those would be a radio detector. So if you get next to a nuclear emitter, you that's undergoing decay, and it's undergoing decay fast enough, and you happen to have like a radio with you, it will actually cause static and popping noises. So just a little side note if you want it. Alright, so this right here is going to be carbon-14 dating, and that's based on the radioactivity of carbon-14 nuclide. Remember, the half-lives are the same for this isotope, right? So carbon-14, no matter how much carbon-14 you have, no matter where it comes from, the half-life is still the same. So that's going to decay by a beta particle production, which is this right here. And so your carbon-14 will slowly disappear from your any substance, let's say an organism, or paper, because paper comes from an organism, or papyrus, which comes from an organism again, by this route, which is carbon-14 breaking down to nitrogen-14. Now, the reason, the secret magic that this all works, is that carbon-14 is continuously produced in your atmosphere when high energy neutrons from space collide with nitrogen-14. So in the atmosphere, nitrogen-14 at a fairly consistent rate is going to be colliding with high energy neutrons, very fast moving neutrons from space, and this actually produces carbon-14. And so the global levels of carbon-14 up until humanity started putting out old carbon due to burning fossil fuels, so the last 200 years, the carbon-14 levels were actually very consistent throughout history. You may wonder how you could know that. That's actually why we had all those missions that went up to the Arctics and drilled in the ice. Because if you drill up sections of the ice, you can actually see gases that were caught thousands and thousands of years ago. And you can actually see how the changes in carbon-14 have progressed over the last, I believe they've gotten back to something in the order of like 40,000 years back. But I think they may have actually gotten further than that by now, but we'll see. I'd have to look that up. Maybe somebody can look it up and tell me. Anyways, so the carbon-14 is actually replaced in the atmosphere. As a living organism, lives and breathes and uses the atmosphere. So most of this carbon in the atmosphere is in the form of carbon dioxide. That carbon dioxide gets picked up by plants and fixed into sugars, woods, all sorts of materials in plants, right? And this carbon-14 then gets transferred along. A small fraction of the carbon is carbon-14. And that's going to be used by anything that eats the plants, or uses the plants to make tools, or uses the plants to make papyrus and then write something on it, right? And so what you know is the atmospheric level of carbon-14. It's going to be a set number for when that organism dies, okay? And that'll be equivalent to the atmospheric level. Now, once that organism dies, your carbon-14 clock starts ticking down. Because once an organism's died, it's not going to take up any more carbon-14 from the air around it. The plant's dead. It's not doing photosynthesis anymore. Once you die, you stop eating plants or the animals that eat plants, and you stop picking up new carbon-14. And so then we have a number to start from, right, which is the atmospheric level of carbon-14. And so you can use this to date wood and cloth artifacts. You can use this, of course, to date human bones, You can use this to date flesh from things. You can use this to date all sorts of anything that's a living organism or comes from a living organism. You can date. Carbon-14 dating will not work, for example, on metals. Anything that's a metal, it will not work on. Anything that doesn't have carbon in it, it won't work on. All right, so the drawbacks to this method. The process requires a fairly large piece of the sample to be burned to form CO2. Actually, these days, this piece of the sample required here is not exactly that large. It's pretty small. It's something that you could take out with a microscope and tweezers. However, you do have to destroy permanently pieces of your sample. So if it is something that's very important, you are destroying pieces of it every time you do a test. So this is going to be then analyzed for radioactivity. This is going to be put in a mass spectrometer. This avoids destruction of the valuable artifact and requires only 10 to the negative 3 gram of sample. And actually, there are newer mass spectrometers that can do less than 10 to the negative 3 grams. However, I do have to warn you, if you ever get involved in this, a mass spectrometer that can detect that level, that less than 10 to the negative 3 grams of sample, those are very sensitive. You have to be very, very careful about the conditions you're running them in. For example, we used to use a very high precision mass spectrometer in one of the labs at KU that I worked with, and that thing was so sensitive that if anybody was smoking on the street across from the building we were in, we couldn't use the damn thing because it would pick up the smoke residue from that person smoking a cigarette. Alright, so the interactive example here is a rock containing uranium-238 and lead-206 was examined to determine its approximate age. And this is how, by the way, you would examine metals and metal samples. You would typically examine this way. You can examine meteorites this way. That's the sort of thing you do. This is also how you can do things like date the Earth. Now, analysis showed the ratio of lead-206 atoms to uranium-238 atoms to be 0.115. Assume that no lead was originally present, that all lead-206 formed over the years has remained in the rock, and that the number of nuclides in intermediate stages of decay between uranium-238 and uranium-206 is negligible. Calculate the age of the rock when the half-life of uranium-238 is 4.5 times 10 to the 9th years. Okay, so this is again a problem that I would recommend you use the integrated first order rate law to do. Just because this is not going to give you nice numbers, and this is going to be much, much faster and easier than just doing half-life after half-life. Now, you can get that from the periodic table sheet I give you for all your exams. So you take this and you plug in your numbers. So you have the natural log of n over n0, the amount you have right now over the amount that you started with. This equals this expression right here, which is negative 0.693 over 4.5 times 10 to the 9th years, which is our half-life here. This is going to be times the amount of time since that was originally there, that rock's age, if you will. So the amount of time since the rock was formed. So let's assume that each lead-206 nuclide present must have come from the decay of uranium-238 atom. So your number of uranium-238 atoms that were originally present has to equal the number of lead atoms that are now present plus the number of uranium-238 atoms that are now present. Because remember, this is going to break down into this. So we're saying that the original amount is what it broke down to plus the amount still remaining. Alright, so we now have here we have 0.115. That was the number given by the problem. This is going to be equal to, well, that's equal to that number over 1, isn't it? Or if we want to do this in a whole number so we can get numbers of atoms, then we'd want to do this 115 over 1,000. So we can get whole numbers here. Because it doesn't make sense to get 0.1 of an atom. That doesn't make any sense. And so we want a whole atom number. So for every 1,115 uranium-238 atoms originally present in the rock, 115 have been changed to lead-206 and 1,000 remain as uranium-238. And so right here we see that 1,000 remain as uranium-238 if we had 1,115 in the beginning. And that would give us a number, a ratio here of 0.8969. Just take that divided by that. All right, so we plug that into the natural log, which is right here, and we go ahead and solve our problem. And we find that time, t, equals 7.1 times 10 to the 8th years. So that's going to be our approximate age of our rock. So it was probably formed sometime in the Cambrian period. That was a long time ago, right? So our rock's very old. By the way, again, remember that first off, we have a number here that is only accurate to 0.1 right here. That means that the error in here is millions of years. We could be off by millions of years because this is already something on the order of, 700 million years. All right, so let's talk about some medical applications for radioactivity. Radio tracers. This is probably the #1 most common use for radioactivity. So this is radioactive nuclides that can be introduced into organisms via food or drugs. The pathways can then be traced by monitoring the substance's radioactivity throughout the different sections of their body or cell. This provides a sensitive and non-invasive method to learn about biological systems, detect diseases, monitor action and effectiveness of drugs, and detect pregnancy in its early stages. Keep in mind, you have a base level of radioactivity at all times. Typically, the amount of radio tracers you put in something simply won't have any real effect. Okay. So right here we see some of the most common radio tracers. An interesting side note that a lot of radiology people, the people that do these tests, really don't know. I recently had one of these done on me, and the person I talked to didn't even know this. These typically come on what are called carrier molecules, which, like iodine, typically comes on a thing that looks a lot like is a benzene derivative. It has several oxygens off it. Anyways, I'd have to show you a picture of it, and I'm not going to bother doing that. You guys don't need to know that. Anyways, these all come on carrier molecules, so they don't come the individual nucleotide. You don't get iodine alone and inject it into a person. This is the half-lives of each of these. This is the area of body studied. For example, iodine typically is used to study the thyroid. Iron, a radioactive form of iron, is of course used to study red blood cells, as in hemoglobin iron. And that's why, by the way, if you don't eat iron, you get anemia. Metabolism is typically molybdenum. The eyes, liver, tumors, this is phosphorus right here. It's very effective for using on tumors because tumors uptake phosphorus at a very, very fast rate, much faster than a normal organ. Anyways, here's some other ones. Strontium is very effective for looking at the bones because strontium very easily incorporates itself into bone structures. And in fact, this is actually the major source of long-term radioactive damage is breakdown to form strontium and radioactive potassiums that then incorporate themselves in the body. Anyways, technetium, heart, bones, liver, lungs. Here's the xenon. Um, sodium. Sodium is circulatory system because you can give them sodium chloride essentially. That's radioactive, and they'll circulate it. Radio tracers generally have relatively what half-lives. Now, this is one of those things that really, if you thought about this a little bit, it would make sense. So if you had an extremely long half-life, would you ever see enough radioactive decay for you to detect? No. No, you gotta sit around for 1,000,000 years to find out if you have heart disease? No. No, you're not. They're not gonna sit around 1,000,000 years to find out if you have cancer. Even 100 years would be too long, right? And so you typically need something that's measured in hours and days. Okay? Days, hours, okay, that actually makes some sort of sense. Years, that's too long. Now you will notice that these are actually not the shortest half-lives. If you have something that measures in seconds, then it's actually going to break down so fast you wouldn't even be able to detect it properly. And so, yeah, you actually short, again, in moderation. So it's hours and days typically. So they're going to be on the shorter end of the half-life spectrum. Okay, so the nucleus thermodynamic stability. This is going to be ascertained by calculating the change in potential energy that results if a nucleus were formed from its constituent neutrons and protons. This is actually where the E equals mc squared that is so famous. And ironically, Einstein is sort of remembered by E equals mc squared, and yet his actual most famous and his real biggest contribution, and nobody realizes it, is why electricity comes off of a fork in a microwave. Which is, you actually saw that in General Chemistry 1, by the way, though maybe the professor didn't point that out. That's actually those electron levels where you're talking about metals having a low, small amount of energy to boost the electron out. That's actually Einstein that came up with that. Anyways, this equation shows that energy should be considered as a form of matter, in fact, or vice versa, that matter should be a form of energy. So, thermodynamic stability and mass. When a system gains or loses energy, it also gains or loses a quantity of mass. Just keep in mind that it's E equals mc squared, right? And so, your c right here is the speed of light, and that is squared. This is a massive number, so very, very small amounts of mass will equal very large amounts of energy. So the mass of a nucleus is going to be less than that of its nucleons, since this process is exothermic. So your change in energy, you could put it as change in E equals the change in mass times the speed of light to the second power. The speed of light is, by the way, a constant throughout the universe. Um, Actually, it's a constant according to perspective, which is a weird thing. And I'm not going to go into it because it's truly some bizarre stuff that you can take some upper level physics sometime or chemistry and learn about. Mass defect is that change in mass, and it's used to ascertain the value of delta E. So let's calculate the change in energy if 1 mole of oxygen-16 nuclei was formed from neutrons and protons. So we have already calculated that 0.1366 grams of mass would be lost in the hypothetical process of assembling 1 mole. Oops. Did I? Shoot, sorry about that. I seem to cut out part of the problem. I don't know what happened to it. Anyways, how you would do that first part where you would get that mass. I don't remember skipping it, so I must have dropped it on my lecture slide somehow. Shit. Sorry about that. Anyways, there's a table of the masses of protons and neutrons in your book. You would simply take that number, you'd add up your number of protons, number of neutrons, uh, and then you'd compare it to the mass of an oxygen 16. And so this would give you, if you did that for a mole, a 0.1366 grams of mass that you would lose in the hypothetical process of assembling 1 mole of those oxygen 16 nuclei from the protons and neutrons. So we can then calculate the change in energy for this process, and we just use this right here, which is the delta E equals delta M C squared. So C is 3.00 times 10 to the 8th meters per second, which is a very fast speed. It's the fastest speed that you can reach in this universe, at least according to relativity. Now, the change in mass is going to be negative 0.1366 grams per mole. We are going to need to change this into kilograms because joules are actually measured in a derived unit from kilograms. And so we take our number here in kilograms, which again is just divided by 1,000 here, and we're going to multiply that by the speed of light squared. So just square that first, multiply, and we get this number right here, which is negative 1.23 times 10 to the negative to the 13th joule per mole. And you will notice that is a massive amount of energy as a negative value, so it's exothermic. And yes, we're talking like a nuclear bomb blowing things up, okay? Or a nuclear reactor powering entire cities and possibly states and countries. Now, computing thermodynamic stability of a nucleus. First, calculate your delta E. Divide molar mass value of the nucleus by Avogadro's number. Amount is calculated in million electron volts, which are MeV right here. So 1 MeV equals 1.6 times 10 to the negative 13 joules. So that you have a relatively modest number you can write for a single nucleus. So next, calculate delta E per nucleon by dividing by A, which is your sum of neutrons and protons. So the binding energy, this is going to be the energy required to decompose a nucleus into its component nucleons. It's going to be the energy that you freed from assembling them, just in reverse, right? So instead of releasing, you're binding. All right, so the iron 56 is going to be your most stable nucleus. This has a binding energy per nucleon of 8.79 MeV. Remember, again, you release energy by binding together, and if you want to split apart, that's going to use up energy. Now, iron 56, therefore, is the most stable one. This is going to be the hardest to break apart of any of the nucleuses. So right here, this shows that same, that's iron 56 right there. It's the highest end of the stability. And here we see this as represented by mass numbers. So what we see here is iron 56 is going to be the hardest one to break apart. Before iron 56, you will actually gain energy by putting those two atoms together. And that's why, for example, the sun actually fuses together hydrogen and helium to a degree, and will actually give off energy from it. It's like a thermic process. So right here, what we see is these want to get smaller to be the most stable they can be, which is closer to iron 56. And so what happens is these undergo fission to release energy. So you break apart uranium-238, for example, to release energy. These, on the other hand, if you break them apart, you will actually use up energy. See that? You get further from the most stable. You're actually going to have to put energy in to make them smaller. Whereas making larger, fusing them together, will free up energy. We'll get to your most stable atom. By the way, this is the reason that iron is one of the most common metals. This is also the reason iron is typically the core of things like stars, especially old stars will have a core of iron, is because it is the most stable nucleus. So excuse me. All right. So let's calculate the binding energy per nucleon for the helium-4 nucleus. So right here we have helium-4 and its mass. So 4.0026 AMU. Right here is hydrogen-1, which is 1.0078 AMU. So first we have to calculate our mass defect, delta M, for helium-4. So the atomic mass, which includes our electrons, are given. We have to decide how to account for our electron mass then. And so there's some mass of electrons here that we have to account for. So that mass of helium equals the mass of the nucleus plus 2 electrons, which is your mass of electrons right here, right? Your mass of hydrogen equals the mass of its nucleus plus only 1 electron. And so that's only 1 Me. So since the helium-4 nucleus is synthesized from 2 protons and 2 neutrons, we see that we get this relationship right here. So our change in mass is going to be equal to our mass of our helium minus, again, this is the total mass of that helium, minus the 2 electrons, minus our 2 hydrogens that we assemble together. This is that total mass minus the mass of electrons. And right here we have our mass of our neutrons, which is 2 times 1.0087. And so we work this problem out, and we see that we have minus 2 here. We have a minus times a minus, so a plus 2 here. Again, that's 2 distributed. And we go ahead and work that out then. The 2 ME's cancel, and we get this. And so we add all of those together, and we get a defect, our deficit of 0.0304. So note, in this case, the electron mass will actually cancel out in taking that difference. This will always happen anytime we do this type of calculation, because the atomic masses are used both for the nuclide of interest and for the hydrogen 1. So it always ends up having to cancel out because we're always just multiplying hydrogens to make whatever element we're trying to make. So the 0.0304 mass lost is per helium-4 nucleus formed. Now I would like to point out that honestly speaking, the difference for those masses of electrons is going to be somewhere in this last decimal point right here. It'll be somewhere in the 4th decimal place. So even if you screwed up, it's not going to be that huge of a deal for most problems. But it will be enough to possibly cause you issues, okay? So don't just go ignoring everything we just did here and just, whatever. I'm just saying that if you do mess up, you're going to have a ballpark number, okay? Now, the corresponding energy change can be calculated by, of course, taking the change in energy equals change in mass, which is our mass deficit right here, times the speed of light squared. And so we put this value in. Again, we need to do this in kilograms. And so we have to do the U of the nucleus and a conversion for kilograms. And that'll be our conversion factor right there. And so we get that many kilograms for our nucleus. This will be the speed of light. We take our number here, which is our mass deficit in kilograms, times the speed of light squared, and we will get this amount of energy for that nucleus. Now keep in mind this is only a single nucleus. This is per nucleus. And so this is quite small, right? This means we have 4.54 times 10 to the negative 12 joules of energy released every time we form a nucleus. And 4.54 times 10 to the negative 12 joules would be required to decompose that nucleus and break it back into its constituent neutrons and protons. So the binding energy per nucleon is this one right here, which is 4.54 times 10 to the negative 12 joules per nucleus, divided by the 4 nucleons that there are in that nucleus, which is this number right here. And so if we want to get that in MeV, which is a more consistent number that is better used for these sort of problems, we will use the conversion factor for MeV versus joules, which is that number right there, which was given to you in previously point in the slide. And we find out that this takes 7.13 MeV per nucleon to break apart, or we'll give that amount when it's formed. All right, so nuclear fission and fusion. I mentioned these terms before, but I didn't give you nice definitions for them. Fusion is going to be combining 2 light nuclei to form a heavier, more stable nucleus. Easiest way to remember fusion is combining small nuclei together is that when you fuse something, or you get a fusion dish, it is combining 2 different elements together, isn't it? Fission, like Fisher, fission is splitting a heavy nucleus into 2 nuclei with smaller mass numbers. Large binding energies will hold the nucleus together. So fusion and fission involve energy changes that are more than 1,000,000 times larger than those that would occur during a chemical reaction. And that's why a relatively modestly sized nuclear device or nuclear fuel gives thousands of tons typically, or at least hundreds of tons of a different fuel, like coal or TNT for explosions. Thousands of times more energy released, thousands upon thousands of times more energy, just 1,000,000 times more energy released when you're talking about a nuclear reaction. Now, nuclear fission. This is an example, of course, nuclear fission. This was actually discovered in uranium-235 nuclides bombarded with neutrons were observed to split into lighter elements. And this is actually the one that it was discovered off of. And probably one of the most single useful nuclear fissions known to man. So this process releases 3.5 times 10 to the negative 11 joules of energy per event. All right, so that's not a huge amount of energy, right? 3.5 times 10 to the negative 11 joules. What are you going to do with that? Well, what you're going to do is a chain reaction. So a chain reaction is going to be a self-sustaining fission process. So what you get is you start off with bombarding it with a neutron. This neutron causes the excuse me, let me get some more. All right, excuse me about that. This will cause your first fission to occur. And so once your first fission occurs, you may have noticed in this right here, you release neutrons. There's actually 2 paths this can take, this uranium splitting apart. It can take this one, which releases 3 neutrons. There's also another pathway, which actually I believe I have in this slideshow up in the first part of it. But anyways, which would release 2 neutrons. And so this uranium being bombarded, it undergoes that fission process, and it releases its own neutrons. Now, these neutrons can then collide with uraniums that are nearby, because remember, you're not going to have just one nucleus that you put in your little beaker or something. You're going to have a piece of metal that's, a few grams. So you're going to have something that's usually a rod or little chunks of uranium. This is going to have many nuclei next to each other, right? And so your nucleus is going to release neutrons, which can then run into other uranium nucleus. And this can then cause another fission reaction. And if that does it again, it can then run into more and cause more fission reactions and more. And you see that you end up doubling or tripling each time. So this is going to very quickly escalate if you don't do anything to contain it. And this is referred to as a chain reaction, of course. So a chain reaction, you have two possible outcomes for a chain reaction. If you're subcritical, that's when you have less than one neutron causes another fission event. The result is going to be the reaction will die out. Less than one neutron causing a fission event means that you don't get a fission event, another fission, for every fission you do. So it'll slowly peter out and die. Now, critical, if you are critical, then that's when one neutron from each fission event causes another fission event. And so at a critical, the result is the process will sustain itself perfectly. It'll just keep going indefinitely at the same level. Supercritical, of course, super meaning more. And so when more than one neutron from each event causes another fission event, this process is rapidly going to escalate. And that means that heat is going to build up and can cause a violent explosion. Of course, supercritical is what a nuclear bomb does. A reactor should be kept at critical, nothing else. No sub, super, nothing, just critical. And of course, if you wanted to stop a reactor from occurring, or you'd go subcritical, right? All right, so critical mass specifies a mass of fissionable material that aids in achieving the critical state. So when you have too small of a sample, the neutrons will escape before they can cause a fission event, and that means the process will slowly die out. And right here just shows you a graphical example. If you have too many nuclei, too few nuclei that are near each other, most of your neutrons are just going to escape away from your sample, right? But if you have a large amount of sample, a very small number of those neutrons will escape, letting you become supercritical much easier. So nuclear reactors, these are going to be devices used to conduct controlled fission reactions. By the way, nuclear reactors could come in two forms. You could have fusion and fission reactors. Interestingly enough, this last month, for the first time, there is a Lockheed Martin actually did it. They patented a working fusion reactor the size of a truck bed, of a semi-truck bed, that can power a town of 100,000 people. There's no information on how much it costs and everything, but yeah, the world just changed. Fusion reactors that you can buy are a thing now, apparently. So that's pretty cool. Anyways, before that, there was only fission reactors that actually worked. They would provide you more energy than you had put in. And these conducted controlled fission reactions. And the resulting energy would then be used to heat water, it would produce pressurized steam, which would then run turbine generators. And this is used for production of energy, not so much in the United States and UK. In most other countries, it's used a lot more because the United States and UK has very powerful, very influential lobbying groups that are extremely against nuclear power, which is very strange. Though, then again, the United States did test its original nuclear weapons by lining soldiers up outside their blast radius and seeing who got sterilized, and then caused about 500,000 cases of breast cancer in Nevada and Utah without telling anyone because they let the fallout cloud just drift through there with never warning anyone that that's going to happen. So I guess the United States government's what they've done to their people has been the cause of our mistrust of nuclear power. Probably. Anyways, this is the basic schematic diagram of a nuclear power plant. Right here you have your nuclear reactor. You will see that this is actually contained under several layers of protection. And so first you have your nuclear reactor. This is going to have your uranium rods right here, and then your control rods that insert between. And what you have here is you have subcritical amounts in these uranium rods here. The control rods then can be moved in and out, and notice that gravity pulls them down. If you stop providing power to this, a good design will cause these to slam down and stop, isolate your uranium rods, therefore giving you a subcritical amount of uranium that won't cause an explosion and actually will stop the reactor. Anyways, so this then has heat being produced from this nuclear reaction. This is going to heat up the water that flows through here. This water in a heavy reactor is D2O, deuterium, which is the isotope that has mass of 2. In a light reactor, this would just be water, regular water, H2O. This water will then be heated up. It'll be circulated through another water bath. Notice these waters never exchange because this is going to have radioactive species in it, which this water is actually quite radioactive. This is the radioactive waste they'll have to collect at the end as well. This then is going to heat this water bath, this water right here. This water is going to be what's heated up and converted to steam. This is under too high of pressure to ever actually form a gas, steam. However, it is supercritical. It is under such high pressure temperature that has reached supercritical typically. This one right here, this tank here, is going to be what the steam that you then drive to your turbine, which will produce electrical output. These turbines, I mean, this figure is very small, but these turbines, this turbine's usually bigger than this entire setup. These turbines are usually huge. Those are going to be what provides you your electricity. Now, this water is actually going to be circulated and is going to be passed by cooling water right here. Notice again, you do not exchange your water. That's so that you can ensure that you do not leak any radioactive water out into the environment. An interesting side note is if you walk past a coal plant, you will get a larger dose of radiation than if you walk past a nuclear power plant. Nuclear power plants actually let off less radioactivity in their surroundings than coal plants. Anyways, so this right here, this is the portion where you're going to cool down your steam and you're going to recirculate that water out through so you can cool this down as well. And this water right here is going to be pumped in from an external source. This is why all nuclear power plants are always built near water. The reason for this entire design, depending on water, by the way, is this design was actually made and that was produced due to a Navy project and was meant to be mounted on submarines and battle and cruisers and all sorts of naval vessels. Carriers, of course, supercarriers are what usually mount them. So the entire idea behind this concept is you're always going to have water available to you to cool the process down. Now, what can go wrong? Well, most nuclear power plants are not built on top of water, which really they probably should. I mean, there really isn't really a good reason. You spend so much money on the damn nuclear power plant, you probably could have just built the damn power plant on top of a dock on top of the water. But anyways, in the Navy design, all of this, except for these pipes down here and the steam turbine, is incorporated into a single, essentially a containment shell, just like this, but it's more contained. It's more, it's sturdy. It's armored, and they literally, when this goes out of control, a naval vessel will drop this entire portion right here into the ocean, and then come back with a submarine and retrieve it. And what that does is it means that this never overheats and causes damage. It doesn't melt components and everything else. So that's your main problem. That's why when you do have a problem with nuclear reactors, by the way, there's only been 4 major events with nuclear reactors, and you probably know all of them. It's not like coal plants that have several accidents every year. Actually, ironically, nuclear reactors don't have that many accidents, but their accidents are very famous when they happen because they cause very long-lasting damage. Now, the 2 parts that you really have to watch out for a nuclear reactor, by the way, are this water right here. You need an uninterrupted supply of water so you can cool this down. Best case scenario, if this cuts off and you're able to insert your control rods, you will not be producing any power. Worst case scenario, you get such a fast cutoff of your temperature and you have damage to this, usually from like an earthquake, like how it happened in Japan. Well, Japan got an earthquake and 2, not 1, but 2 tsunamis that damaged their damn power plant. So that was actually really just terrible luck. Really unfortunate. But anyways, of course, the major concern is your control rods. To control this from becoming supercritical, you need to be able to insert these control rods. Typically, that would happen automatically, and there'll be a manual control as well. If you stop providing power to this in a very good design, some of the ones I've seen before, they would automatically insert. However, there's also typically also a manual that somebody can literally just go in there and insert them. However, every now and then, these control rods, when accidents occur, typically it's due to the fact that these control rods get overheated, so it causes them to fuse, so they can't get inserted, or they get damaged in some way or another. And so then they go supercritical, and that's your problem. And that's your big issue here, is when it gets overheated and you can't insert your control rods, that's typically what happens. Alright, so your reactor core, that's this one right here, that's going to have your coolant with your uranium fuel cylinders and your control rods. This is going to house uranium-235, which is the one we use in most nuclear reactors. You can also use plutonium and several different other isotopes, but uranium-235 is the most common one. This is enriched to approximately 3% in the cylinders. Anything below that, you start getting too low of a concentration to get a critical mass to keep that chain reaction going and giving you power continuously. The moderator, this is a device that will surround the cylinders and slows down your neutrons. Typically, these will be things like lead rods here or some sort of alloy. This will enable the uranium fuel to capture neutrons efficiently. Anyways. I'm sorry, the moderator is actually a chamber around it. I guess I skipped forward on me when I was doing this. Sorry about that. Moderator is usually sort of a chamber around it. It's sort of cylinder in shape, and essentially what it does is it helps you slow down those neutrons so you can more efficiently get this uranium fuel to capture the neutrons and undergo the next fission. Your control rods, these are going to regulate your power level of the reactor. They're also going to help you stop any supercritical chain reactions. These are going to be composed of substances that are efficient at absorbing neutrons. Typically, just very dense materials, very dense alloys. They're going to help control malfunctions in a fission event. The rods are inserted into the core to stop your reaction when they're fully inserted. A breeder reactor. This is going to be a device that produces fissionable fuel while the reactor runs. So the reaction involves the absorption of a neutron and produces two beta particles. And that's what you're seeing right here. One of the major ones that you want to make is things like neptunium, plutonium. Keep in mind that a lot of these radioactive materials are actually very high value materials. For example, all fire detectors have a radioactive material in them called americium. So, reaction process. As the reactor runs, uranium-235 is split. Excess neutrons are absorbed by uranium-238 to produce plutonium-239. Plutonium-239 is separated out and used as fuel for another reactor. So this reaction breeds nuclear fuel as it operates. The disadvantages of this is that there are a lot of hazards in handling plutonium, and it is very expensive to process and recover that plutonium, especially if you do not have the proper facilities. Fusion reactions. These are capable of producing tremendous amounts of energy as well. The sun is a very, very large fusion reactor. So the sun produces large quantities of energy by the fusion of protons to produce helium. And of course, you can also fuse protons, produce, this is deuterium right here, which is the mass 2 hydrogen. This is actually the helium right here, which is actually the isotope mass 3. And this is the helium you're more aware of, which is the 4-2, the atomic mass 4 helium. Helium-4. So here's some of the stumbling blocks with fusion energy production. Frankly speaking, there are many advanced topics that we could talk about. You could do a whole class easily on fusion with no problems at all. But some of the major stumbling blocks, why the sun works and we can't do it on Earth very easily, is you need to reach a very, very high temperature to initiate fusion, so that the individual atoms are moving very fast and collide together with the amount of energy needed to fuse them together. The protons should be closely bound together to release energy. These protons are identically charged and they repel each other electrostatically, so it's very hard to get them to stay contained in one area. They want to, go away from each other because they repel each other. And so they will explode away from each other very easily if you don't spend a lot of effort and energy keeping them all contained together. They must be shot at each other at a speed that can overcome this repulsion. So, right here is a plot of energy versus your separation distance. The hydrogen 2 nuclei must be sufficient velocities to get over this electrostatic repulsion hill right here. This should be close for the nuclear binding forces to effectively fuse the particles into a new nucleus. Large quantities of energy will be released if you can manage this. Now, really before about a couple of years ago, it wasn't really even that close. We were not able to get efficient enough. We were not able to do these processes efficient enough, keep it at a high temperature with all these protons near each other to effectively create a fusion reactor. All the previous fusion reactors actually used more energy than they made. However, apparently that was solved. It was solved by, actually I've seen 3 projects that have solved this and look like they'll probably work, but Lockheed Martin's came out of nowhere and I didn't even know about that one, to be honest. And they've done it. They have a working fusion reactor that provides more energy than it uses. And the cool thing about fusion reactors is ultimately you're making helium, which is inert and actually is a high price target, something you can use, and is actually a useful product. And the really cool thing is you can get the hydrogen from seawater. And so you have lots and lots of hydrogen that you can process given enough energy to make fuel. So as long as they can get this cheap enough to make the reactors itself, this is actually going to be a huge deal. Really game changing, really world changing. Anyways, I don't know how cheap their reactors are. So, which process is likely to occur when the neutron to proton ratio in a nucleus is too large? That's, of course, fission. So, again, when you have a ratio, a neutron proton ratio that's too large, you're likely to split up so you can get rid of some of those protons to get that ratio back down. Which of the following is true regarding the fission of uranium-235? Ultimate nuclides nuclides produced are more stable than the uranium nuclide. So the nuclides that you produce, of course, have to be greater stability than the nuclide that you split apart. That's why they form, that's why they released energy. If more than one neutron from each fission event causes another fission event, the fission situation is described as supercritical. That's when it's supercritical. Alright, so here's some effects of radiation. We can have somatic damage. Occurs to the organism itself. Results in sickness or death. Effects appear immediately if high doses of radiation are received. Alright, so somatic damage is essentially you've damaged cells and organs in the organism, and so you see immediate damage. You see immediate effects if you have high enough doses of radiation. Now, genetic damage, this occurs to the genetic machinery of an organism, so the DNA, and that causes malfunction in your organism's offspring. This can also, of course, cause things like cancer as well, of course, because you're doing mutations in the DNA. You're damaging the DNA, which can cause mutations. So the biological effects of a source of radiation will depend on the energy of the radiation, the penetrating ability of the radiation, the ionizing ability of the radiation, the chemical properties of the radiation. So first thing you need to understand and note is REM, which is the Roentgen equivalent for man. This accounts for your energy of the dose of the radiation and its effectiveness in causing biological damage. It's going to be RADS, which is your energy level for the radiation, times the RBE, which is your relative effectiveness of the radiation in causing biological damage. And that will give you REMS. By the way, a lot of people have seen RADS before because there's a very famous video game that has RADS in it, Fallout, or video game series, I should say. And yes, those RADs literally are this RADs right here. That's what you're seeing there. So it's a lot of you actually are somewhat familiar with this to a degree. Now, right here we see several different REM doses. If we have a 0 to 25 REM dose, we'll have a non-detectable effect, clinical effect on our organism. Notably, this would be on a human biological system, which would be a human organism, right? Yes, cockroaches have much better resistance to radiation than humans. Though, interestingly enough, dung beetles can actually live inside of a reactor in terms of radiation. They're incredibly resistant to radiation. Go figure. Anyways, 25 to 50, this gives you a temporary decrease in white blood cell counts. 100 to 200 rem would be a strong decrease in white blood cell counts. Really, at this point, you've probably destroyed that person's immune system. 500 rem would be death of half the exposed population within 30 days after exposure. Now, this is directly just going to kill that organism because of organ failures and their skin sloughing off. But this right here, 1 to 200, you will actually, most of the organisms that have this level of exposure are going to die as well. Most of the, I say organism, but we're talking humans here, would die due to infections because you've destroyed their immune systems. 25 to 50, unless you give them white blood cells to replace, by the way, which is how they actually do some autoimmune diseases. They destroy your immune system to then give you a new one, usually from a relative. So 25 to 50, this temporary decrease in white blood cell counts, this is enough that actually it can cause some serious clinical effects if you're not existing in a vacuum. But this won't usually kill the person. This will just cause some issues. This right here, this non-detectable effects, yes, within 30, 60 days, you're probably not going to see any effects. But in reality, if you have 25 rem radiation dose, you probably just increase your risk of getting cancer by a considerable amount. Okay? Once you get up to 25 to 50, you've really improved your risk of getting cancer. One exposure isn't going to be such a huge increase in risk of getting cancer that you're going to get for sure, I think. But it's like smoking, a few packs of cigarettes. You're going to have a much higher risk. All right, so radiation hazards. Nuclear power plants pose a serious potential for radiation hazards that can be caused due to accidents that permit the release of radioactive materials, improper disposal of radioactive products. An interesting side note is this is one of it's about 15 years almost that we did not have proper disposal in the United States of radioactive materials. It was almost the entire George W. Washington Jr.'s presidency and Obama presidency that we did not have proper channels to dispose of radioactive products. And we literally just built them up for almost 15 years in temporary storage facilities where they were much more likely to to leak and everything else. It was really a disaster. And the funniest part about this is, it's not really funny, but you gotta laugh because it's so sad, is that the reason that was originally blocked and they couldn't actually get rid of those, they couldn't produce new facilities to make them, is because, okay, so the radioactive materials were already in the storage pools, which were in major cities. And so when they tried to transport these materials out of the storage pools that are in the major cities into storage, long-term storage, and then processing centers, which are away from the cities and people, the people in those cities protested those transfers and didn't allow them to transfer it in a series of legal lawsuits. So to keep those radioactive materials, I quote unquote, away from them, they trapped them next to their water sources and them. It's just a case of, it's like McDonald's getting protested 4 times in the last 100 years to change what they fry their fries in. It's because it's more healthy. And then every time they found out later it's less healthy. And sometimes they knew it was less healthy at the time period. Some protests are just not well thought out. This is a very good case of that. Anyways, they now have proper disposal activities, and there's processing centers now that recycle most of the radioactive products and actually make further products from those. In fact, one of the weird things that you probably didn't realize is the uranium 238, the depleted uranium, is actually used to make rounds for heavy caliber guns and stuff, armor piercing rounds. And it's actually increased the Middle East radiation, background radiation level to almost double what it was before. So it's a, it, I guess it's nice the recycling, but it's not a very great thing that's happening due to it. But oh well, that's beside the point. That's anyways, it's kind of interesting thing to have in the back of your head. So some of the models for radiation damage, we have the linear model. So damage from radiation is proportional to the dose, even at low exposure levels. So any exposure will be dangerous in a linear model. The other model is the threshold model, which honestly, from the data I've seen, the threshold model is probably the more realistic one. The linear model, almost as far as the data I've seen, is almost certainly not, uh, has almost certainly been disproved. Yeah. Anyways, they of course do not sit people down in front of radiation sources and test these models, but there is some data out there. Actually, most of that data from the USSR and the United States when they were testing nuclear bombs. So that threshold model is going to have no significant damage occurs below the level of a threshold exposure. So as long as you're below the threshold, you won't have any significant effects from your exposure. So right here, these are the two models of these radiation damage and a nice graphic. Whoopsie. I guess you know the answer to that one. So, which of the following is not a factor in determining the biological effects of radiation exposure? The energy of the radiation, well, that certainly is a factor. That's the rads, right? B, age of the organism that suffers the exposure. Well, the age doesn't really matter. C, penetrating ability of the radiation. Yes, the penetrating ability of radiation will matter a lot because if it can penetrate it to your organs, that's going to cause a lot more damage than if it can't even penetrate through your skin. The chemical properties of the radiation source. Well, you're not getting hit by the radiation source. You're not being reacted with the radiation source. You're getting hit with the radiation, right? So it doesn't really matter what chemical that came from. The radiation is all that's going to matter. Ionizing ability of the radiation. Okay. Let me go ahead and make a few notes here. That apparently I need to throw some. None of this notes I'm going to give you are going to be on exams or anything. Um, they aren't particularly important parts, or I felt that they didn't really need any greater explanation, at least for use in exams. However, there is one little factor that I do feel is there's a couple factors that I feel are useful for your understanding if you ever go to work in any place that has radiation exposure risks. And that would be things like hospitals, actually, which have radiation units. So, first off, how do you detect radiation? I mean, I know I showed you scintillation counters and Geiger counters, and you could use those, of course, but any film, like film that you would use for a camera, you know, those old film cameras, can actually be used to detect radiation. And that's how the radiation was originally detected on a photography plate. Now, if you have film and it's in the presence of radiation, it will start developing the film, and the film will change color. Okay? Typically, it'll get darker. And you can actually get films that are colored. They'll turn like a blue, red, different colors depending on their exposure levels. But typically they just use a film that will get darker and darker as it's exposed. Now, what does this mean? Well, first off, you need fresh film every time you go into an area. So if they give you a badge, make sure that you get a new one when it's supposed to be replaced, okay? Because they will develop over time. And you'll think you're exposed and you're going to die, and you're okay. Number two, the penetrating power of different types of radiation. So we talked about the different emissions before. We had the alpha, beta, and gamma, right? Now, alpha, these are actual nuclei, right? And they're going to be fairly slow compared to the other two forms of radiation. So if you were exposed to an alpha particle source, then you could hold up a piece of paper between you and it, and that will actually block all the alpha particles. So even a piece of paper would block alpha radiation. Now, beta radiation is a bit more penetrating than alpha. And so beta radiation is typically blocked in the first few layers of your skin. So alpha radiation won't even penetrate through your skin. Beta radiation would actually get blocked by the time it gets to the fat layer. So typically beta radiation's effect on a living organism, as long as you don't breathe it in or otherwise get it inside your body, is fairly limited. Now, gamma radiation, that's the killer, okay? So gamma radiation typically takes a layer of a few inches of lead or usually a yard or so of concrete and steel, which is why you see like bunkers have like a few feet of concrete and steel. And that's actually what's required to block gamma radiation. Gamma radiation, of course, is very small, it's neutral, and it's just very, very high energy photons. Now, typically when a nuclear bomb, I used to give the inner workings of a nuclear bomb in my lecture, and then I got pointed out that was not good. Anyways, I probably still could. It's not like anybody's gonna be able to actually create it from the inner workings I gave you guys. Still, it's probably not a good thing, and you don't need it. Anyways, if a nuclear bomb ever goes off, hopefully it won't, in the near future, hopefully that's not a thing anymore. That will happen. Anyways, if it goes off, the thing that vaporizes people is the gamma radiation. And then the heat wave, of course, will also vaporize them. But the gamma radiation is actually your big killer. And that's what causes the most casualties. The alpha and beta particles don't cause any real casualties. Now, what causes the area to not be inhabitable later is actually the daughter nuclides, the species that are made from those nuclear reactions. So you have the nuclear reactions, the one on the reactant side is the parent. The one on the product side is called the daughter. And so those daughter species, those can hang around and break down over time. And that's what will cause an area that's had a nuclear bomb go off or had a nuclear accident like 3 Mile Island, that sort of thing, Chernobyl, to be radioactive for an extended period of time. It's all those daughter molecules that are breaking down over the next decades, hundreds of years, sometimes thousands of years. And if you don't do anything, and how you do something about them is you literally dig the soil out and dump it somewhere where it won't cause any harm. So if you don't do anything about it, an area that's been contaminated with those daughter ions will stay radioactive for typically hundreds of years. For a World War II, Cold War era nuclear bomb. A modern United States nuclear bomb, the figure I have been given before, which I don't know how accurate that is, and I hope we never get to test that, is it would be, you could go in there, you'd be safe enough to go to for soldiers to go in that area within about a day or two. And then the place would be safe for inhabitation within a couple of years. The figure I've been given for somewhere like North Korea is they're still back in the Cold War era, hundreds of years. It's yeah. By the way, an interesting little side note to all this is you may have heard of the 2 bombs that were actually dropped in warfare were by the United States to end the the war with Japan in World War II. And The first one we dropped was actually a fusion bomb. And that one is actually, the effects of it are mostly gone from the area. It's safe to occupy again. So that's actually kind of a good thing. That you can go back in that area now. They have a museum there, by the way. That's all uh, about nuclear war and the war between the United States and Japan during World War II. And I hear it's actually very nice. Anyways, you guys have a great day. Have a great time. Take care and good luck.